Okay, welcome to Unit 24. We talk about substitution. This is a integration method, and the plan is I make 4 parts. Task, second the method, third the drill, and the 4th part is the challenge. There are 4. The task is, first section is the task. Remember that we wanted to compute an integral like e to the minus x squared dx. So that was appeared as a, and we computed the mean of the normal distribution. So how do we integrate this? And what we do is we have this integral x times e to the minus x squared. What we can do is we can identify part of the formula which we call a new variable. For example, here we can take x squared and we call this u. And I usually kind of make just a little substitution cloud here. U is equal to x squared, and then I differentiate with respect to x. So that's, but I don't actually, I put the dx on the other side. I say d2x, that's the derivative, dx. So du over dx is 2x dx. And the reason is because I want to substitute also this dx. So that's the du over 2x. So we make this kind of a substitution. That's called a substitution. And so if we do that, we get the x we leave just for a second. So this is e to the minus u. And the dx, which we have here, that becomes the du over 2x. So there's a cancellation here, right? This x really cancels away, and so we have no x anymore. So this is integral e to the minus u du, and we have e to the minus, this is, we know how to integrate, this is minus e to the minus u, and plus c. And now we can back substitute minus e to the minus x squared over 2. So we have actually the du over 2. I forgot the 2 here. And that was our answer. That was our answer here. So that's a example. And I just want to identify a couple of things we have done. So in the first part we have done we have found substitution formula. Then we have plugged it in and we have simplified, we have integrated here, and then we have back substituted here. So that's the method, and we practice this today with many examples. So that's the method. This is part 2, the method of substitution. You will see when we do examples how this works. So let's just run right into examples, as many as we can. First example A is just the integral 1 over square root of x plus 1 dx. So in this case, and usually when we have something under a square root, you just want to call this u and make this substitution cloud. U is equal to x plus 1, du is equal to dx, and we substitute everything in. So we get 1 over square root of u, and the dx becomes the du. And we know how to do that. That's just the 2 times square root of u plus c. And now finally we back substitute 2 times square root of x plus 1 plus c. That was example A. Let's run with example B. So that's an example, and you might already have guessed what we take. So when we have we take this as our u, and so maybe I just use a little bit of brighter, less bright color. So we have u is equal to 2x plus 5. Du is equal to 2 dx. Then we can say dx is du half. So that's our substitution. And let's continue with the computation. That's the integral of cosine u. The dx becomes the du half du. And we know how to integrate cosine u, right? That's sinus u half plus c. And now we back substitute, which is sinus, and then 2x plus 5 over 2 plus c. That's our result. Let me just run right into a little bit more challenging examples and not make too many examples because it's again such a beautiful day here. So I just take this example, tangent square root of x over square root of x. So if you think about this, it's natural to take the square root of x. What else would you substitute? Because the square root of x really appears in two places. So we take u is equal to square root of x, and then the du is 1 over 2 times square root of x dx. I usually leave that. I don't put anything in, substitute u in here, but we can see whether this works. So we have the integral, and then we have the tangent of u over u, and the dx becomes the 2 times square root of x. And we have a cancellation, and we have the integral 2 times tangent u du. Now you might just know what the integral of tangent u is. Why don't we do that, kind of continue with that on the next page, make it a little bit slower. We can again do that with a substitution. So we have the integral 2 times tangent u du. If we pretend we don't know what the integral of tangent u is, so this is sinus u over cosine u du. And again, we can make a substitution here. The substitution which works is, let's call this v. So v is equal to cosine u, dv is equal to minus sinus u du, and du is equal to minus dv over sinus u. And you see that kind of works pretty well, because if we go into the equation, so this is equal to 2 times, so that is actually the sinus u du is actually just a minus dv, so it's a minus sinus. Cool. So that's our example D. And what did I prepare before? Oh, log x, that's a beautiful one. So that was D, that was E. Now we have the integral of x. So what shall we substitute? Usually, what is a good thing to look for? So maybe I just write that down. So to look for, what we want is to have a situation like this. So that's actually just g of u of x, where g prime is equal to g. And so that's kind of a situation you want to look for. And in this case, then you see that you actually want to use this as u. I cannot stress enough this thing. If you kind of see this situation here, that you have a function of u and then the derivative of u, then this works beautifully. Example F is the integral of tangent x over cosine square x dx. So we had just seen this advice, you know, remember the advice? We want to look for a function and its derivative, and we know a function, right? This is actually a function we know the derivative of, and if you take this u, this is just the d, this is just the u prime, this is the derivative. So that's what we try. Sometimes I have to try different things. So we get tangent x, and then we take du is dx over cosine square x. So that's exactly what we have here. That's actually the du. We take this u, and that's our substitution. Now we are in business, right? So that's the integral u du, which is and I prepared some tougher examples. So this is part 4 of the presentation. So the tougher examples. For some reason they are tougher. Sometimes it's just harder to see what to substitute. So I have this example dx. Until now we have just seen always that we took just essentially, you know, you would take the u is equal to 1 plus x to the 4. That would be a natural thing, or x to the 4 would be natural. But then you get the du, you get an x to the 3, and you get the messy thing. So that's not good. So here you have to kind of have a better idea. U equal to x squared really works here very well. And it's harder because it's harder to guess this substitution. So we 2x dx. But somehow what we want is really kind of, we want to have the du appearing, and actually that's really the du, and that's maybe the hint which works. The function becomes more complicated, but we can live with that because we know what we have. So this is now du over 1 plus u squared, and that's a function which we know how to integrate. That's the arc tan u plus c. So this is the arc tan of x squared plus c. So sometimes a little bit of flexibility helps. That's example A. Example B, what did I prepare for B? Okay, I take this example, the integral of x to the 3 and the square root of x squared plus 1. Yeah. Oh, that's a tough one. I actually will stop with this one. This is really a tough one. This is a pickle. So it's not obvious what to take. But in general, it's always a good idea, first of all, to try, if there is a square root, to try that under the square root. That's what works here, but it's not obvious. So we take u is equal to x squared plus 1. So we take du is equal to 2x dx. So we take this as our substitution. And it's not obvious how this actually will pan out. But let's just see what happens here. So we have the x to the 3, I leave that x to the 3, the dx is actually the du over 2x, and then we have the square root of u. Let's just see what we can do. We can simplify a little bit here. So we get an x squared. We are not yet really there because we have that x squared, but we know that x squared plus 1 is actually just u minus 1. So that's why I consider this a difficult problem, because it's not so obvious that you see that this is actually, still now, it's not so obvious why you should see that this works. But it works because you can actually take it apart. You can say u over square root of u minus 1 over square root of u. And both of these we can integrate. So this is square root of u minus 1 over square root of u du. Minus 1 over square root of u du. So we know how to do that. That is u to the 3/2 times 2/3 minus 2 times square root of u plus c. And now we can back substitute the whole thing. So u was the square root, u was the x squared plus 1. So what we had is u was equal to x squared plus 1. So x squared plus 1 to the 3/2 times 2/3 minus 2 times x squared plus 1 plus c. So we got through, but it was not obvious, and so we have sometimes just to try, and if it doesn't work, just try something else. And that's it for today.